Okay, triple integrals. And I say why, because why not, right? You do double integration, you do triple integration, and believe it or not, there's actually quadruple integration, which you probably won't ever see because that's in 4 dimensions, and you go higher in dimension itself. So that's a full-on, only theoretical kind of portion. But for now, there's actually a concept in 3 dimensionals called triple integrals. So what do triple integrals actually do? Okay, so a triple integral is basically if I have a surface, so for example, let's suppose I have a cube in 3 dimensions. Okay, so therefore I'm going to cut a portion out of this cube. Okay, and that portion is literally just a cube itself. Right? So you could think of all these stacked up cubes everywhere. So if I just cut, and just stack them all together, that becomes a volume. So the triple integration over the XYZ plane literally gives you the volume of the surface itself. Okay, and it's pretty straightforward. The theory behind it is like it is: find this volume of this cube, and then you're going to add all the cubes accumulating the entire surface, which gives you a Riemann sum in 3 dimensions. So the sum of I to 1, I to infinity, j to infinity, and k to infinity of this volume, which gives you a very particular theorem called the Fubini's theorem of triple integration. And we'll just start from the easier one of a box. We'll go to regular proportions in a little bit, but the box is usually the easiest one to start with going forward into general regions. So give it a box where it's A to B. So for X is from A to B, Y is from C to D, and R is from, or Z is from R to S, this little individual box itself. Then the triple integral of this first surface gives us the volume in terms of all 3, X, Y, and then Z. So let's try to put this to practice, give you guys an example of how you do triple integration. It's exactly the same as just double integration. We're just going to do it 3 times instead of twice, like double integration actually is. But let's try this out. So let's find the triple integral over this rectangular box where we're given X is between 1 and 0, Y is from -1 to 2, and Z is from 0 to 3. So if we set up this triple integral, and we're going to go from X, Y, Z. So Z is on the outside, Y is in the middle, and X is first. Like that. So we just integrate normally. So now first with respect to X. So this is going to be X squared over 2, YZ squared. Evaluate it at 0 and 1. 0 just is nothing, so it just evaluates at 1, so we just get the 1/2, and I'll put that on the outside of the double integral. So this is just a constant of y squared dy dz. And we just rinse and repeat. So again, take the integrals now with respect to y. So be y squared over 2, z squared evaluate now at -1 and 2 this time though. So I'll bring this 1/2 on the outside. So now it's a 1/4. And if I plug in 2, so 2's on the gone, so it'll be 4. And I plug in -1. That gives me positive, so it'll just be z squared. Well, that's not that bad. Ends up being just 3 z squared. So this ends up being the integral of 0 to 3 of 3z to squared, dz. And that just gives you 3 to the 3rd power times 1/4, evaluate 0 and 3. And 3 to the third power is 3 times 3 is 9, 3 is 27. So this ends up being 27 over 4. So just a quick little example how you do triplet integrals. Okay. Now, just like it was for integration with respect to x and y, so we can also do all the other types of scenarios as well. So we can change our bounds of integration. Instead of doing x, y, z, we could do y, z, x, or z, y, x, or the other type of combinations. Now, to do so, however, there's different types. So there's technically 3 different types of triple integration. Okay. The first one looks like this. So where z is in terms of strictly x and y. So the easiest way to figure out is if the surface we're integrating goes up and down. Okay. So therefore, usually x is the last thing to do, and y is in terms of x, and then z is in terms of both x and y together. So these are 3 different examples of when that is actually true. Okay. Now the next type of portion is, well, what if we flip it? Okay. Oh, and this is the other, like the 3 different ways we can have it. So z is only in terms, like I said, of x and y, or y is in terms of that portion, or I can just flip it around and have y at the end, right? So there's 3 different ways we can use type 1, 2, and 3. Now, type 2 is what if x, I gotta misplace that, what if x is in terms of that? So only x is in terms of y and x. So these surfaces go along the xz plane this way. Or sorry, the yz plane this way. Because everything else is in terms, so you get to give x being constant. Okay. Well, same process, right? You take the integral with respect to x first, and then dA is either y next or z next, or wherever you go from there. And the last type of it is, well, what if it goes through the y? So everything's in terms of y. So this surfaces go this way. So it goes on the y scale itself. Okay. So therefore, you would do y first, and then again either x or z and x respectively. Okay. The key thing when it comes to these type of questions is figure out what type you're actually in, and then from there just figure out what are your bounds of integration going to be. And that's that's the most difficult part, is figuring out what you're going to be doing from that. Okay. So let's try an example so you can see how this would work out. Okay, so let's evaluate the triplet integral of z dv, where E is a solid of the tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, so let's just see what's going on. So our tetrahedron looks something like this. And it's shaded all the way to the origin 0, 0. Okay, so that's what we have so far. So we want to find this triple integral, so we got to find our bounds of integration, and then go from there. All right. Well, let's say we want to do normally what? So dx, dy, and dz, for instance. Or actually, let's do the other way. Let's do dz, dy, and then dx. So therefore, dz, that means we got to first solve for z here. So z is going to equal to 1 minus all of this. So therefore, we know z is bounded between 0 on the x-axis to 1 minus x minus y. Now let's look at, remember, so because we have z first, therefore, we're only going to be looking at the xy plane here. And if I just look at the xy plane and I just bring it up to here, it's this rectangle right here. It goes from 1 to 1. That's what this bottom plane looks like here. So now we just got to figure out what this line represents here. You can do it two different ways. You can find the line of the equation, y-intercept of 1 and find the slope. Or you can just set z equals 0 here and just solve for y. And you just get y is equal to 1 minus x. So if we integrate this way, so y has to go from 0 to 1 minus x, and x goes from 0 to 1. So now we have our triple integral, where x is last, y is in the middle, and z is first. Right, now we just take the integration with respect to z. So that's going to be z squared over 2, evaluated at each one. And again, like everything else, you plug in 0, it goes away. So it really just depends on the first part. So I'll bring that 1/2 again at the very end on the outside. Okay. And if you really want, you could FOIL this out. I'm not going to do that. I'm just going to use, like we did before, just use substitution. So I'll let u equal the entire thing. So we just get -1 dy. So I just pop a negative to make it positive. So therefore, if I take the integral of u squared, that's just going to be u to the third over 3. So again, bringing that 1/3 out and that 1/2 gives now 1/6. And then this time we're evaluating this whole thing from 0 and 1 minus x. So if I just plug this into y and this into y, this is cubed, sorry. So we get 1 minus x minus 1 plus x minus, plug in 0, 1 minus, this is third, x to the third. Times the 1, all this times the 1/6. Last thing is, these cancel. So you just get 0, which is great, right? And this negative, this negative is still there. And then the negative makes a positive. So this ends up being 1/6 the integral from 0 to 1 of this dx. And again, so now I'll just rinse and repeat the same thing as use substitution. So pop the negative on the outside again. So this ends up being that. So bring out the fourth, that's 1/4. So -1/4, 24. Evaluate at 1 gives you 0. You plug it in 0, you get 1. So you get 1 over 24. Okay. Now, for this particular example, you could actually done it 3 different ways. So this one we did z/yx. That's one way. And you can actually do it all 3 ways. So now this time, we're going to do it with respect to dy, dz, then dx. So you can see you get the same result. May get a little bit more difficult integration, but it's to get the same result either way. Now, if we do with respect to y, z, and x, therefore we have to go back up to here, to our surface, and change our variables. So now instead of z equaling this, we have to solve for y. So now our bounds of integration is going to change a little bit. So if I solve this with y instead now, I get y is equal to 1 minus x minus z, and that's going to be your top function, so 1 minus x minus z, and that's still going to be between 0 and that, because I'm now going this direction instead of going up. Okay. And now since I integrate with respect to y first, now when it comes to the other two variables, I have to look over here and just look at the x and z plane. So x and z plane are right here. So if I transpose that, this now becomes this. And again, this graph, this function here going from 0 to some value, it's the same thing as just plugging in 0 in for y and solving for z. So we get z is equal to 1 minus x. And again, x is still bounded between 0 and 1. And now we just now do this integration with respect to our new bounds. So dy, dz, then dx. So first with dy, next with dz. So you notice our bounds of integration changes a little bit, and even then our integral is actually going to be much different than what we have here. So for example, right, so we take the integral with respect to y first. That means we just have a y, because nothing, z is nothing with respect to y itself. And now, right off the bat, you can tell it's going to be something already different. Plug in 0 for y, goes away. So this ends up being the double integral of z times all of this. Already a bit different. So take the integral with respect to z. Now again, plug in 0. They all go away because I'm plugging in for z, and then just plug this in, and this ends up being 1 minus x squared over 2 minus x times 1 minus x squared over 2 minus 1 minus x to the third over 3. And we take this integral from 0 to 1 dx. Again, already far different, but very similar. So what I'm going to do is I'm going to put these together. So this portion right here should give you 1 minus 2x plus x squared. So if I just tweak this a little bit and put these together, and this negative changes everything, right? So we negative x times all of this. Gives me that. Okay. All right, so I'm going to take the integral with each thing individually. So for example, integral of 1/2 is just x over 2. Integral of this is just going to be minus x. Well, I'll just do the whole work so you can see. And over here, or you could just factor out the 1/2. You get the, get the same result. And over here, I'm going to use the fact we already did it, which is right here. And this whole thing is being evaluated at 1 and 0. A little bit more of a mess, but you end up getting the same results. So you can go back and redo it now and just do the last one. Do x first, and then do, if you want, let's say dy and dz, or you flop these ones around if you like as well. Either way, you would get the same results, which is kind of interesting. Okay. So when you cannot do that, that's the worst part. So when do we convert stuff to make it much easier? So let's say, for example, we have this situation. So we want to find the triple integral of this bounded by y equals x plus z squared and the plane y equals 4. Okay. So there's a nice little picture of what's going on here. Now notice it's going this way. Little hint for later. Okay. So let's see what's going on. So if we want to do, for example, like we did last time, z, y, and then x. Okay. Okay, so in that case, I have to solve for z here. So then z is equal to plus or minus the square root of y minus x squared. So that's what z is bounded between. And it makes sense, right? If this is the z plane, this is the y plane, and this is the x plane. So z is bounded between here and down there. Minus. Okay, so now we got to figure out y and then x. Okay. So again, if z is 0, we just get the parabola y equals x squared. So this is y equals x squared. And it stops at y equals 4. So here's my y equals 4 plane. So therefore, what's my bounds for x? Well, if I plug in 2 in for x, I get 4. Or I just set them equal to each other to solve for x. That gives you 2 and negative 2. So x goes from negative 2 to 2. All right, so now y goes from 0. Or actually, that's from 0. From the parabola up to 4. So from x squared to 4. So we have our triple integral of this whole thing. dz, dy, dx. And z goes from this to the positive. Y goes from x squared to 4. And then from negative 2 to 2. Now, hopefully you realize this is an absolute horrible mess to deal with. I actually have no idea how to integrate this. Right, this is bad. Okay. So now, maybe we did it wrong. Maybe we should not do with respect to z first. Maybe a different variable would be better. Okay, but this was our hint I gave you earlier. It's going this way. So why don't we do it with respect to y first, and then we'll figure out x and z later. Okay, so if we do it with y first, that means I go back up here, and now solve for y. Wow, look at that. It's already done for me. Well, that's kind of nice, right? Okay, so y, we'll just change our bounds now. X and z. So now y goes from where to where? So y goes from here to there. So it still stops at 4, because that's the maximum it goes, so it still ends at 4. And it starts our actual function, x squared plus z squared. Starts here, goes up to there. Okay, good. But now we want everything in terms of x and y. Or yeah, x and z. So x and z is this plane here, right, this plane. So if I project it onto here, how do I do that? Yeah, so if I project it, I get a circle. In fact, I just get that. Okay, so now remember, we want x on the outside. We'll just say that's easier, x out. So x goes from, from here to there. So same thing from -2 to 2. But now what if our z goes into it? Well, that just means I'll just solve for z, because it gives me the upper half and then the lower half, which almost gives me exactly what we have here, right? Solving for z. So subtract x squared and take the square root. So z goes from 4 minus x squared now, inside the square roots, instead of just y. Okay, so if I go down here, our bounds of integration, respect to y, z, and x, go from y first, so it's going to be from x squared plus z squared to 4. Then goes from z, which is the square roots, and then finally x. Okay. Which still looks like a horrible mess, but it actually is not that bad.